My name is Burkan Isgor. I'm a professor at Oregon State University. My partner in crime, Jason Weiss, is also here, so we'll be happy to answer any questions after the talk. Today I'm going to talk to you about a little bit about the science of PLC. Now, I think all of us here are very familiar with how a clinker reacts when it starts hydrating with water. So in the left figure, you can see that these black and gray scale shades at 0% degree of hydration as are the clinker phases. They start getting consumed as your degree of hydration increases. That means that you're basically waiting, the concrete or paste is aging, and as they're consumed, you actually start forming all the good stuff that we like in concrete. You produce CSH, which is the glue that holds things together. You produce calcium hydroxide that partially gives that high pH, high alkalinity to your concrete, which has other benefits for concrete. You produce monosulfate, again, that helps your porosity, etc. Some part of it remains as water, and you get some chemical shrinkage. Now, if you don't want to know, if you don't care about those phases, you can also look at the right figure where you can see as you produce cement, you produce some solids, gel solids, which are the good stuff. Now, some of those gel solids also contain water. We call those gel water. And you have capillary water. So you can partition your system as some good solid phases, some water, etc. Then all the good benefits that you get in concrete through cement hydration is shown here. Now, when you have limestone in the system, so when you start adding limestone to the system, things change, and they change quite a bit. Now, in the left figure, now we have the horizontal axis, the limestone content, going from 0 to 30% by mass, and the vertical axis, as we showed before, those phases that we care about. Now, if I'm not going to show you a time-dependent case, let's take 90 days of hydration as our snapshot point. At 90 days of age, we can look at 0%. This is exactly what I showed you in the earlier one. If you look at the 90-day degree of hydration, you will see some CSH, you will see some calcium hydroxide. That green thing at the corner, triangular thing, is the monosulfate, and you have some water. Now, when you add limestone to the system at 90 days, you actually see something interesting happening. The monosulfate that we have in a clinker-based system starts basically disappearing after a couple of percentages of limestone addition, and that converts itself to ettringite. So you start ettringite instead of monosulfate forming ettringite. That's a pore filling phase, so your porosity should get some assistance. And on top of that, the yellow phase here is that you start forming some hemi and monocarbonates. That's also a pore filling phase. So interestingly, that means that in the first couple of, like it's maybe 0 to 5% addition, your porosity should get better. And that's what we see. And you can actually see this as well. If you look at this sharp change here, that's actually indication that porosity is decreasing. But as you get higher limestone contents, you're diluting your clinker. So you're not producing as much CSH. So your clinker content relates to CSH content. So you can see a slight decrease in the CSH content. And you can see also here the solid phases, those beneficial phases, are also decreasing. So this means that that beneficial initial decrease in porosity will start getting worse, and your porosity is going to increase. Now, this is summarized in this figure, where the vertical axis is your porosity, and the horizontal axis is your limestone content by mass. As you can see that this star represents the clinker, or the old OPCs, where we didn't have limestone at all. So you can see that porosity here is somewhere here, let's say 37%. A couple of percentage points of limestone addition decreases the porosity relatively sharply. And as you start keep diluting the system with limestone, you start producing less CSH. You have unreacted limestone in the system, so your porosity starts increasing again. But the thing is that initial decrease gives you quite a bit of buffer to add more limestone. If you look at, for example, about 15% addition, you get pretty much similar, chemically similar porosity compared to an OPC that doesn't have any limestone. So the logic behind limiting 15% limestone in the 1L cements is basically that 15% porosity more or less corresponds to 1L, a typical OPC that we have these days. Now, or we had without limestone. Now, the thing is that, as I said, at 15%, you also have diluted your system, so you have a little bit less CSH, but we want to get very similar strength from these 1L cements. So in order to compensate for that decrease in that beneficial CSH, we basically grind the cement, intergrind the limestone with cement a little bit more finer, and that is intended to give you the equivalent strength as before. Now, something interesting happens to this scenario when you start adding SCMs. There was a very good presentation before, and we see that you can actually decrease your clinker content significantly if you actually incorporate SCMs as well. But not all SCMs are created equal when it comes to PLC. So if you think about a system where you're increasing your limestone content from 0 to 30, and if you think of 100% reactive silica, which is basically what typical SCMs would have, reactive silica, and you can see that the benefit of adding reactive silica is not very obvious. You get some initial decrease in porosity in early limestone addition, but this has nothing to do with reactive silica. It is just what I just showed you, conversion of monosulfate to ettringite aminocarbonates. But when you look at the case where you add a reactive alumina in the system, reactive alumina, you can see that has a huge benefit in reducing porosity. So if you put any point, let's say look at this point, it's 30. If you look at the corresponding point in this one, it's 36. So you get significant benefits of reducing the porosity by just using some reactive silica. Now, you can also see this, what's happening. What does reactive silica do? Reactive alumina do? Reactive alumina basically consumes the calcite. These plus are unreacted calcite. You can see that unreacted calcite amounts are significantly lower when you look at a system with reactive alumina compared to a system with reactive silica. So when you have alumina in the system, reactive alumina, you're actually consuming your limestone. The concept that we always were taught that limestone is an inert material actually is not correct. Limestone reacts with alumina. Now, those simulations were all, those data were all simulations, thermodynamic simulations. You may say, I don't trust thermodynamic simulations. Give me some experiments. So we have done that as well for Caltrans. We did a very large project, and we can see these experiments. There's OPC systems, OPC plus fly ash, OPC plus fly ash. Again, I'm very sorry. These are not OPC systems. These are PLC systems. I apologize for that. So these are PLC with different systems. And these bars represent for each one, there are different admixtures. So we're not going to get into that. But you can see that these dark shaded content represents how much reactive alumina you have in these systems. The amount of reactive alumina, let's say in this case about 2%, corresponds a lot with how much calcite is consumed. So this is a proof that reactive alumina is a very important component of these systems. And this is summarizing that as these lines, so the black line was what I showed you earlier without any alumina, reactive alumina. But if you increase your reactive alumina content, you can pull down the porosity more initially, And that gives you more opportunity to add more limestone in your system. So you can see that even beyond 15%, you can achieve porosities that you wouldn't have achieved if you didn't have reactive alumina system in the system. Now, this is a great opportunity because some SCMs we use have reactive alumina. Slags would have them, calcine clays would have them. So there's a great opportunity. This is just to show that those of you, who are very curious about if you compare an OPC versus PLC, you can see that you actually get pretty much the same pH. I told you that CSH would decrease a little bit. Again, that decrease is not very large, especially if you have alumina in the system. You're producing calcium alumina silicate phases, cash phases. So that is also not bad. So by grinding it finer, we actually make a huge, we get a huge benefit. Now, I'm going to switch gears at this point. Now, we have seen that PLCs are able to provide very comparable porosity and strength to OPC. And we can also use some SCMs to our benefit, especially the SCMs that have reactive alumina in them, to actually make things much better. Now, how do we do this, though? How do we optimize a mixture? How much limestone we should have in a mixture? How much SCM we should have in that mixture? Is a complex problem. It's an optimization problem. First of all, as we were told, not all PLCs are the same. And the second, not all SCMs are the same. And every SCM has a different composition, and every SCM has a different reactivity, pozzolanic reactivity. So in order to incorporate these materials in a mixture that's optimized, we need to have a tool. So at Oregon State University in the past 10 years, we have been working on developing such a tool. The idea is based on a modeling framework that allows us to predict the key properties of a paste or a mortar or concrete using very basic information, as basic as a chemical composition of your cement or PLC and the chemical composition of your SCM that you're using, and supplemented by the reactivity of the SCM to separate the reactive components of the SCM from unreactive components of the SCM. I'll talk about the reactivity a little bit more later, but once you know those, we can use thermodynamic calculations, as I showed you before, to determine how much CSH we have in the system, how much calcium hydroxide we have in the system, how much porosity we have in the system. We can partition gel porosity from a capillary porosity, and with all that, we can predict properties like compressive strength, formation factor, which is a transport property, calcium hydroxide content, time to critical saturation, pH, and many more. Now, we have this tool in our hands that you can just give us the chemical composition of the materials that you're using and the reactivity of the SCMs that you're using. We can predict those properties. I'm not going to go very deep in this. Obviously, this is not that presentation, but I just want you to rest assured that we have been doing significant amount of validation, and you can see here that this experimentally measured porosity versus predicted porosity on the horizontal axis. That one-to-one line is basically the black line, and we are very close to that one-to-one line with our framework. Same thing about formation factors. I can give you many more validation points, but just want you to understand that this framework helps us to predict properties. Now, that gives us an opportunity to proportion these mixtures really well. So I'm going to take you a step-by-step approach how we use this framework to actually optimize a mixture with PLC and SCM, ideally containing a reactive alkali phase. So in this step one, we characterize our materials. What does that mean? You have to run some XRF or chemical composition analysis. You have to know your PLC composition, and you have to know your SCM composition. You can see that this SCM has quite a bit of alumina in it. Now, with SCMs, we also need to know how much of that SCM is reactive. So we have a pozzolanic reactivity test, which is summarized here. Basically, you take your SCM, put it in contact with calcium hydroxide in a high pH environment. That reaction is a pozzolanic reaction. It releases heat, and it consumes calcium hydroxide. If you plot your heat release versus calcium hydroxide as a point. That point corresponds to an equivalent degree of reactivity that tells us how much of that SCM is going to react and how much is not at infinite time. So we actually have this test. This is something that we need because we need to quantify this very accurately. Now, this second step is define the performance criteria. So we want to proportion our mixture for a specific performance. So let's say I want to design proportion a mixture for a bridge deck. That means that I want to achieve at least a 5,000 psi strength. I want a formation factor of 375 or higher, and there are other criteria here for corrosion resistance. This time to critical saturation, 30 years minimum, is for freeze-thaw resistance. So you can define a performance like this. You can define for a Midwest pavement. You may define a foundation with different criteria. So after you define your performance, then let's say we are trying to proportion a mixture with those materials using follow the criteria defined for a mixed Midwest pavement. What we do is basically use that modeling framework that I just mentioned as a virtual test bed. So we run many simulations. It can be tens of simulations or hundreds of simulations or thousands of simulations. It's up to us. The horizontal axis shows you a range of water to binder ratios from 0.35 to 0.55. So in this range, we can have, let's say, 10, 100, 2,000 water to binder ratios. The vertical axis represents the SCM replacement level. And that goes from 0 to 50% SCM replacement. Again, we can bracket this into 100,000, whatever number we have. So for each case with PLC, we replace the SCM at this water to binder ratio, and we calculate different properties. So in this one, we ran, let's say, I don't remember exactly what this was, let's say 10 by 10. It means that we ran 100 simulations. For 100 simulations, we plotted the data for strength. And you can see that there are these lines. A line here, a 25 MPa line, tells me that any mixture along this line, any mixture of water to binder ratio versus at a certain replacement level has a 25 MPa strength. Now, my criteria was I want a 29 MPa strength. So 29 MPa line is this black line. So any mixture on this left side of that black line, this triangle, would satisfy that strength criteria. So I can use any mixture here. Any point here will be okay. Now, I can do this for any other criteria that I have. So if I do this for formation factor, this is the line that represents the formation factor of 270. And the left side is showing me all the mixtures that would have a 270 and higher formation factor. I can do that for calcium hydroxide content. That might be relevant for a Midwest pavement because we worry about calcium oxychloride damage, and calcium hydroxide content is important. We don't want a lot of calcium hydroxide in the system. So anything lower than 20 grams per 100 gram binder is good. So anything above this green line is fine. So we do the pH, we do time to critical saturation. At the end, we can find a zone in this water to binder ratio to replacement level plot where this shaded area represents any mixture in that area would satisfy the performance criteria. So we have a tool now that we can take a PLC and say, okay, I have this SCM with some reactive alumina. How much of that SCM I can use to satisfy a certain criteria to deliver a concrete that would work for that application? So this is basically what we have achieved and what we have been developing over the years. Now, one thing that is beyond that is that what I just showed you, that feasible area, is technically going to satisfy all these criteria, but in this area, there are infinite number of combinations of water to binder ratio and SCM replacement level. So which one should I use? So you have to have additional criteria. So one additional criteria is, okay, choose the material that will minimize my carbon footprint and cost, right? So you can actually say, I want the least cost and the most carbon footprint, carbon dioxide reduction. So we also implemented that optimization algorithm where you can specify the cost of the materials. We know what carbon dioxide cost is. So let's say your SCM is free. There's nothing free in this world, but if you assume that SCM is free, you will automatically know that the best option is use as much as possible, feasibly possible, so that you reduce your carbon footprint to the minimum, and that means that you go and choose. So this is the feasible region here, so you use as much as possible. But if your SCM becomes expensive, it gets a little bit, you have to pay for it. Now, using as much as possible may be good for the carbon footprint, but it may not be the best for the cost. So in that case, this optimization algorithm shows that this circle here is your point where you should optimize or do your mixture proportion. If it gets more expensive, you may actually use a lower replacement level and a higher water to binder ratio. So again, this is an additional thing that we have done. So the conclusions that I have is that PLC produces concrete with similar chemical composition to OPC concrete, and these ettringite, hemicarbonate phases, and monosulfates replacement. So ettringite replacing monosulfate, they help the porosity initially. Now, after a while, you start diluting the system, but up to 15% with intergrinding, a little bit finer, you can get equivalent strengths, as we saw. Additional alumina is very interesting. The SCMs that contain reactive alumina makes PLC is a very exciting material, and we can think about how to optimize those mixtures with PLC and SCMs containing reactive alumina. And I just showed you a way of doing this in a very scientific way. And I hope you enjoyed this presentation. I'm happy to answer any questions. Thank you.